Problem 21 in section 12.1. We have the Mega Millions is a multi-state lottery in which players try to guess the numbers that will turn up in a drawing of numbered balls. One of the balls drawn in the mega ball, matching the number drawn on the mega ball, increases one's winnings. During the recent 3 years period, the mega ball was drawn from a collection of 15 balls number 1 through 15, and a total of 344 drawings were made. For the purposes of this exercise, we group the numbers into 5 categories, from 1 to 3, from 4 to 6, and so on. If the lottery is fair, then the winning number is equally likely to occur in any category. Following are observed frequencies. So the question gives us the table and they give us the observed, and they're asking us the question A, B, C, D. So you notice that the question A, B, C are the leading question or the guide question for us to answer the last one, part D. So if you perform the hypothesis test, and that means the whole thing, that you answer A, B, C. So for this problem, we have 5 categories. We have, this is 1, 2, 3, 4, and 5. And this is uniform distribution. How do we know this uniform? Because we have 5 categories, so the chance to each category occur to be the same. Okay, so 1/5, right? 1/5, 1/5, 1/5, 1/5. So this is similarly like a dice problem. So under the new, you will write down the expected frequency, expected probability, the expected probability. So you expect the probability from 1 to 3, from 4 to 6, from 7 to 9, and so on is equal to 1 over 15. And the opposite statement for that is one of them is not equal to 115. It can be more or can be less. So the short way to write is at least one is different. Now step number 2, we find the expected value. So this is the frequency observed frequency. So they are the observed. What does it mean by observe? It means you look and you write down the result, but the problem already write down the result for you. What do you expect is that the total draw is 344, so it should be divided equally for each category. So we have 5 of them, so that will be 1/5 of this. So the expect is 1/5 of this number. The formula that we learned from the book is expect equal to n times p. So the n is 344, and the p for the category 1 to 3 is 1/5. And that's what it means. So this is 1/5 of the total. After we got the expect frequency, we put in the table O and E, and we know we have a formula is O minus E squared divided by E. So I just plug in the number and I divide. So I subtract first and square and then divide. But before that, we will write down the observed. Those numbers are given from the problem. Those are the expected number that we just calculate. And we use the formula. The formula to find chi-square is the sum of O minus E squared divided by E. So we add this number up and we got 1.7267. Now we have the next step is calculate the critical value. For this section, we only have critical value. So we have The degree of freedom is k minus 1. K in this case is the categories. So we have 5 categories. So 5 minus 1, so it's 4. So you go to the GeoGebra, you input 0.05 for the alpha. And you will input the alpha is a right tail. We always use right tail in this chapter. So 0.05 and we got 11.0. The degree of freedom is 4 and we input 0.05. So we got 9.4877. So 9.4877 is the critical value. The test statistic value is 1.7267, so it's land on the plane region, and it's land on the non-reject, right? So we do not reject. The shaded is reject, but the blank is do not reject, so we do not reject the null. Now let's go back. If we do not reject the null, that means we are keeping the null. We keep this. So what does it mean? This is the expected probabilities, right? Okay. So we have the expected probabilities. So what do we expect the probability to be? Is equally chance for each category. So 1/5. So answer the question. The question asking us. The question telling us that if the lottery is fair, then the winning number is equally likely to occur in any categories. And we keep the null, and it shows the expected probability. So in part D, they ask us to test the hypothesis that each of the categories is equally likely. So we say that each of the categories is equally likely for the conclusion. Now for this problem, if we want to use the GeoGebra, we must calculate the E first, the expected value first, and then we input the observe. So here we go to statistic. We will choose the goodness of fit. Goodness of fit for chapter 12, 12.1, and chi-square test will be 12.2. Okay, so we can change now. So we have 5 categories. For the blue color shaded, you can put out a name like from 1 to 3 and so on if you want, but it's not needed. Okay, what do you do is you put down the observe is given in the problem is 73, 64, 74, 62, and 71. The expected count is the 1/5 of 344, so you can do 344 divided by 5. And of course, it's 68.8 we calculate already, right? 344 divided by 5. 344 divided by 5. 344 divided by 5. Or you can just put in 68.8, okay? So either way. Now, you see that the total 344 for both observed count and expected count, and we should get that, always get that, okay? Then that means we are right. Okay, now you look in the chi-square, the value is 1.7262, and that is exactly the same manually work that we did. And if you want to use the P in this case is, in your book, they don't do the P, they only do critical value for this chapter. But if you use GeoGebra, you can get the P is 0.7859 compared with the alpha is much bigger, right? So that's why we do not reject.